Today, what Franklin saw as the electric atmosphere is seen in modern terms as the electric field. An electric field is present around any object that carries a net electric charge. Of course, if an object's positive charge and negative charge are balanced, the object is electrically neutral, and it produces virtually no electric field far away. But even beyond that, the static electric field inside any piece of metal is zero, which means a test charge would feel no force at all inside the piece of metal. And that's true even if the metal has a net electric charge. That's because the charge piles up on the surface until there's no field left inside to make it move. Of course, electrically charged conductors do create electric fields outside themselves. But inside, there's no field at all. And because there's an electric field between two oppositely charged pieces of metal, there's bound to be a difference in potential between them. But since there's no field inside, the potential is the same everywhere in the metal. So, each piece of metal is a region of constant potential. The potential difference between two pieces of metal depends on how much net charge each one has. Negative charge lowers the potential. And positive charge raises the potential. Of course, in the 1700s, Dr. Franklin was in no position to get such a clear picture of electric potential, for even its concept was unknown in his day. But he did have an enormous knowledge of electricity, which he often shared with his colleagues throughout Europe. And as the wisest American, Ben Franklin also paid considerable attention to the great minds of the past, particularly Sir Isaac Newton. Franklin was well aware of Newton's theory of universal gravitation, and he knew the force of Newton's gravity unites the universe by causing masses to attract each other. Franklin would have liked to formulate a similar law, a law of electric force. But it doesn't quite work, because unlike gravity, there are two kinds of electric charge. Electrical charges that are unlike attract each other, and charges that are alike repel each other. That's one reason why an ordinary battery has the potential to create an electric field.
When a battery is connected between two pieces of metal, it forces charge to flow from one to the other until the potential difference between them is equal to the voltage of the battery. That creates an electric field between them. If the voltage is doubled, so is the charge. So is the potential difference. And so is the electric field. In general, the charge transferred is proportional to the voltage applied, and the constant of proportionality, C, is called the capacitance.